Hi everyone, my name is Patrick and we are the ASTIC Microgrid Power System Team, short for AMPS. This is everyone. We're going to step out now. SDG&E has sponsored our team to design a portable analysis tool to simulate a miniature power grid system. Now you might be asking, why does this matter? Well, it's important to educate people about the harmful effects produced by non-ideal components found in power systems, such as inverters, and the problems they introduce back into our power grid. Now, there are many people nowadays switching over to renewable energy sources, such as solar. But what they don't know is that there are many inverters out there that don't produce an adequate sinusoidal waveform. So, to give you an example, if you use a modified sine wave inverter, and you plug in your cell phone charger or turn on your LED lamp, you will increase the total harmonic distortion. As a result, this will also increase the power consumption, heat dissipation, and more importantly, it may reduce the lifespan of your electronics. With our analysis tool, we can plug in any common household item and display the current along with the harmonics coming along with it. So as you can see behind me is our physical model where we can plug in any load onto the faceplate. You can also see our graphical user interface where we display all our harmonics and currents and can be plugged onto any PC. Now Abdul will explain to you a little more about the user interface.
Thank you, Patrick. Our user interface is used to connect hardware and software together. We use it to control hardware components. I'm going to walk you through the GUI now, then explain the two main software features we have. Before we start with the hardware controls, we have to press the connect button to connect the GUI to the hardware. And then we have two choices for our inverters. We can pick from a sine wave inverter and a square wave inverter. Our user interface supports adding a filter to the system. And then for the loads, we switch in a load that we want to see the harmonics for. Our system can read from one load, two loads, or even three loads at a time. As for our software features, we have a save data feature to save data we want to come back to in the future and see. And our load feature acts as a simulation for the saved data. I will pass it off to Bashar now, and he'll talk about the faceplate.
Okay. Hello, everyone. My name is Bashar Amin, and I'll be talking about the design of our model. So for our model, we are using a Pelican case. It's a portable box, easy to take from one place to another if we want to test. And inside that box, we integrated all of our electrical component, and on top of the box, we have the faceplate. So the faceplate is our main control panel. As you can see, every input is labeled and has an LED indicator. So we have 3 AC outlets and we have 3 filter inputs to test for our load with a filter. We also have labels for the pure sine wave inverter and the modified sine wave inverter. And we have a plug-in for the battery charger to charge our model. And we also have a mini switch to turn the model on and off. Next slide, please. So this is what goes underneath the faceplate. We have 3 mini PCBs that are connected to a main bus board that is connected to the battery, the inverter, and the Raspberry Pi. Each one of these mini PCBs is going to be connected to an AC outlet, and each one of them will have a relay, a voltage sensor, and a current sensor. And Jeff will be explaining more about these sensors. Thank you.
Thank you, Bashar. My name is Jeffrey, and I designed these sensors. So in order to get those nice looking waveforms you all saw in the GUI, what we need to do is sample the currents and voltages in our AC system. So in order to do that, we use some very simple shunt and series resistor topologies. In the example here, you can see a shunt resistor that is going to create a small differential voltage across it as the current flows through it. We then take those small differential voltages and feed them into a 2-stage amplifier. The first stage of our amplifier is the AMC 1100. We selected this unique chip from TI because it's an isolated amplifier, so the input stage is electrically isolated from the output. And this allows us to keep our 120 volt AC system separate from our low voltage electronics. After that, we take the output of that amplifier and feed it into a pretty standard op amp. We use the Microchip 602, or MCP 602 here. And we use that to do a little bit of level shifting and further amplification to get our signal into a perfect 0 to 3.3 volt range, which can be sampled by our microcontroller, which Luke is going to tell you about next.
Hello everyone, my name is Luke. I'm here to talk about our microcontroller. So our microcontroller performs three main functions, the first of which is the ADC peripheral, short for analog to digital converter. So our microcontroller is connected to the three sensor boards that Jeff just covered. It's also connected to our main bus board and our battery, where the ADC peripheral will allow it to sample voltage and current waveforms at a rate of 4 kilohertz. So to sample these waveforms for 3 full cycles, which roughly estimate to 200 samples per node, all of this data will be stored in our microcontroller and forwarded to the Raspberry Pi via the UART peripheral. Our UART is configured at a rate of 14.4 kilobytes per second, which is the maximum rate that allows for accuracy. Together with the ADC peripheral sample rate and the UART peripheral, it allows the user to experience a 2-second screen rate refresh. And the last peripheral that I'm going to talk about is the GPIO peripheral, which allows our microcontroller to set the relays and essentially allow the user to select between components such as our inverters, our loads, and our filters, while simultaneously also setting our LED connected to these respective components, which are on our faceplates, so it allows the user to easily recognize which component is in use. I'm going to pass it on to Daniel to cover the communication flow.
Thank you, Luke. So you might be wondering, how does AMPS actually communicate with our user interface? Well, for that, we're using a Raspberry Pi. We use a Raspberry Pi because it offers onboard Wi-Fi, which allows us to easily connect and send and receive data wirelessly through Python socket libraries. So some of this data we send is relay information, such as setting toggling loads on or off and having filtered or non-filtered output, and also selecting between the sine wave inverter and the modified sine wave inverter. Additionally, we send data request to the Raspberry Pi. This data request is forwarded through UART to the microcontroller, which is storing all the sensor data. This data is then packetized by the Raspberry Pi into a nicely formatted text file, which is sent through the socket to our user interface. Our interface parses that file, performs calculations on it, and displays our waveforms. To talk about what's actually powering these electronics, I'll pass it off to Nicholas.
As you can see, this is the bottommost layer of our model. It has a battery and 2 inverters. As per the requirements given to us by SDG&E, we were required to have a model that would run for an hour without being plugged in. To accomplish this, we picked a lithium iron phosphate battery. And the reason we picked that battery is its high energy density over its nickel, cadmium, nickel metal hydrate, or lead acid batteries. We use this battery to power the 2 inverters, which Ben is going to talk to you about now.
Hello everyone, I'm Ben. So in our system, we used 2 different types of inverters, one pure sine wave inverter and one modified sine wave inverter. And the purpose of this was, say for example, we want to see the different harmonic contributions from using different types of inverters. So let's say, for example, you're a homeowner, you want to save some money on your electricity bill, so you decide to install some solar panels into your home. And let's say, you want to be kind of cheap, so you decide and get a lower quality inverter. Well, the drawback with using that lower quality inverter is most likely it will produce a modified sine wave output, which will create more harmonic distortion in your system. In turn, as mentioned before, this will increase power dissipation in your electronics, shortening their lifespan, as well as in the long run, it's going to cause you to maybe swap out whatever system it was in a sooner amount of time. So you may save some money up front, but it's going to cost you more in the end. So to demonstrate this, here you can see that we have a very pure sine wave inverter, and using a very powerful and common known analysis tool like MATLAB, we plotted these data points taken from an oscilloscope in the frequency domain in MATLAB, and to verify, this is our verification that our user interface could reproduce fairly accurate the results taken from an oscilloscope and using the computation from MATLAB. Next slide. So here's the output from a modified sine wave inverter. As you can see, the modified sine wave inverter contributes a higher amount of harmonic distortion. And again, as mentioned, this increases the power dissipation in your electronics and shortens their lifespan. So now to talk about filtering, I pass it on to Andia.
All right, thank you, Ben. So I designed the filter for our overall system, and like many power systems, our model can facilitate the use of a filter. And why do you want to use filters? So in the end, the use of a filter, it'll reduce the amplitude of the harmonics that you saw on our previous slides. And by reducing the size of reducing the amplitude of these harmonics, you can reduce the total harmonic distortion in the overall system. And overall, you can expand the lifetime of some of your household items. And so for our design, we decided to design a low-pass filter, which will essentially block out some of the higher harmonics, starting at the 9th harmonic at 540 hertz. And by doing so, it will reduce the total noise in the overall system. And next will be Amar talking about our system block diagram.
So to tie it all together and to give you the overview again, the main components of the system is the battery, the 2 inverters, a pure sine wave and modified sine wave, and 3 plug-in loads. We have multiple relays. We have a relay to select between inverters. We have relays on each of the loads to turn on and off the loads. And we have relays to select between filtering and non-filtering. We have multiple sensors. We have a main voltage and current sensors. We have, each of the loads has a sensor for currents. All of the sensors and the relays are connected to a microcontroller. The microcontroller and then connected to a Raspberry Pi via UART. And the Raspberry Pi is connected to the PC, which has a user interface via Wi-Fi. And the system is isolated from the grid. So when the system is off, you can charge the system, charge the battery of the system. Once you turn on the switch for the system, it's going to be solely powered from the battery. So it's going to power the low voltage components and the high voltage components from the battery. And next, Josh is going to talk about the milestones of the project.
Thank you, Amar. I'm Joshua. Here are our milestones that we use as an outline to efficiently and effectively complete our design. Both the hardware and software team worked in parallel in order to complete these milestones and to optimize our effectiveness. There was some obstacles that hold us up with the milestones that we didn't complete on time. But we collaborated as a team, and we worked together to complete our project on time. Here's Sabi with the budget.
Thank you. So I would like first to thank SDG for the budget and for the support for the whole semester. Thank you so much. So the allocated budget was, as you guys can see, $1,000. And the highest use of the budget went to the enclosure, and then for the hardware team, and then for the software team. And we went over budget about 213 because, we went over budget about $200 because we had to do the enclosure box, which cost us about $300 extra. And in order to meet our project design, we had to pay this. And thanks for the professor and for the school for covering up. And I will pass to Patrick.
Thank you, Sabri. All right, so just to wrap things up, we've designed a miniature power grid system that analyzes non-ideal or the damages done by non-ideal components. We've shown you how the negative effects of using modified wave inverters and using a pure sine wave inverter, which only shows the first fundamental harmonic. We also have explained how we can start solving this problem by using filters to start filtering or mitigating out those higher frequencies. Now, without further ado, we'd like to thank San Diego Gas and Electric for sponsoring this project. We'd also like to thank John and Mark for helping and mentoring us out through the semester. We've learned a lot. We had a great time designing this project. And I hope you guys learned something new today, as the whole purpose of this project is to teach people. So thank you.